This is session B7, Experimental Studies of a Weak Interaction, the Scientific Legacy of Stuart Freedman. Stuart was an outstanding experimentalist of his generation who died suddenly last December in the middle of his career. He was an exceptional physicist. His insights, his critical faculties, his ingenious ideas for experiments were unique. He also had a marvelous sense of humor, which worked both pedagogically and was tremendously enjoyable. He's greatly missed by many of his colleagues, both for the field as a whole and personally. It is very appropriate that we have this session. I should mention that there is a memorial fellowship, graduate fellowship, being set up at Berkeley in Stuart's name. And if any of you are interested, in, just Google Stuart Freedman Fellowship at Berkeley. Our first speaker is an old-time friend, I'm not sure, I dare say mentor of Stuart's, Gerald Garvey. And he'll give his talk on some issues there.
Thank you, John. So I'd like to thank the organizers of this session for inviting me to speak. I'd also like to thank this organization for arranging for this session to be videotaped so that Stuart's widow, Joyce Freedman, can get a sense of what's transpiring today. So my vantage point in dealing with Stuart is really quite different from those of the two very talented young men who will follow. I encountered Stuart long before his rare talent had become widely known. And in many of those interactions, I was what you might call his boss. That's not the easiest position to deal with Stuart in. But throughout all our interactions, we were very close friends. You'll notice, those of you who have read the abstract, that I really changed what I'm going to talk about. I took a look at much of the early research that Stuart did, some of it with me, and decided that it really wasn't all that interesting. And what I'm going to present to you today is material that I think more fully represents just what Stuart became well known for. So I want to start with that very remarkable PhD thesis that Stuart did. It was a test of local hidden variables. This is a picture of Stuart in the laboratory of Gene Cummins with the apparatus that Stuart used to actually prove the first example of a John Bell's inequality dealing with the issue of hidden variables. So it was remarkable in the sense that it was the first experimental demonstration of one of Bell's inequality. It experimentally resolved an issue that had been going on in physics, admittedly somewhat in the background, from some 40 years. Einstein was a firm believer in the fact that God didn't roll dice and believed that somehow there were hidden variables that made the outcome of experiments more deterministic than quantum mechanics would allow. What the experiment involves, the measurement of the polarization correlation between a pair of entangled photons. The photons are entangled because they proceed from the two photons proceed from a state that's in angular momentum zero and end up in a state with total angular momentum zero. So their spin should be correlated. So if you move the polarization angle of the, say, the second detector with respect to the first, you expect to see something that can be determined either by quantum mechanics or by hidden variables. The paper shows an application of Bell's inequality that says that the polarization that you measure at 22.5 degrees minus that you measure at 67.5 degrees minus a quarter has to be less than zero. And if this were violated, it would show that there were really no hidden variables. So the experiment starts out, it was realized that one had to use atomic transitions because the photons at those lower energies were they were much better polarization sensitive polarization sensitive detection. And so the experiment involved atomic calcium, where one formed an excited 0+ state that emitted a dipole photon to a spin 1- state, and then the photon is emitted from the unperturbed intermediate state to the ground state, and one would have expected there to be a correlation in the polarization of those two photons. The apparatus was, really relatively complex. The excitation of this more highly excited state is done with just a discharge of a deuterium lamp. An atomic beam of calcium is formed, and it is set up so that it decays in front of a pair of filters that selects the energy of the photons, and the polarizers are set, can be set at definite angles, and you measure via coincidence that correlation. This is what Stuart measured. This number should go up when the two polarizers are closely aligned to a number nearer 1, but the efficiency of the polarizers was such that they got a number more nearly 1/2, and at 90 degrees one saw a great decrease in the correlation. The number that was measured, this quantity delta, was indeed a positive number, and by something like 5 standard deviations, it showed that the Bell's inequality did not hold, and hence hidden variables which would have predicted a distribution like this was shown not to be the case. So no dice. Or maybe I should say dice, because that's quantum mechanics. So Stuart's experiment showed that it was violated by more than 5 sigma. Quantum mechanics is essentially non-local, and there are no hidden variables. There was some criticism of the result because necessarily at that time the experiment was somewhat inefficient. The coincidence rate with the polarizers removed was the order of 1/10 of an event per second, and there was a fair amount of background. Subsequent measurements using lasers, where you split a photon by a down conversion and then couple it back together, shows rates in excess of 1,500 per second, and in 5 minutes they had more than 100 sigma violation of the Bell's inequality. I can't comment. This was, I would say, the first example of an entangled state where you showed that quantum mechanics properly did the entanglement, and I can't tell you what the impact of that was on today's enterprise dealing with entangled states. So that was the first clarification, and I have to admit that those of us who were in the nuclear physics group at Princeton didn't fully appreciate what Stuart had done. It was widely appreciated by Eugene Wigner and Johnny Wheeler. Stuart came to Princeton. It's the first time that I met him, in 1972, and you can see him standing here in the photograph. Many famous persons are in the front row. I'm over here somewhere in the company of Jim Peebles and Dave Wilkinson, who is behind. It's an interesting and nice photograph. So the early experiment that Stuart got involved in at Princeton was the following. It was the issue of a thing called second-class weak currents was a hot topic in the early 70s. Second-class currents involved certain transformations that would occur under the G-parity transformation. I don't want to go into it in too much depth here, but it would cause FT values for certain beta plus and beta minus decays that you would have thought should be the same to differ slightly, but the effects were small. They're the order of the beta energy divided by nucleon mass. The experiment at Princeton that Stuart got involved in measured the correlation of a beta decay momentum with the spin of a neon-19 nucleus, characterized by the spin here and the beta momentum there. That gave an energy-dependent spectrum in this mirror decay, and it was, in many ways, I thought, the best understood of the measurements that one could carry out to sense the existence of a second-class current. So the paper was published in PhysRev Letters. Stuart's name is there. It's quite an elaborate enterprise. You make the neon-19 using the Princeton cyclotron beam. The neon-19 is separated out from the other products that come from bombarding the sulfur hexafluoride, and the radioactive neon-19 is injected into an atomic beams machine. Stern-Garlock is used to select spin up and spin down, and you introduce the polarized neon-19 into a detection region that was viewed by these two scintillation detectors. The result that was found was surprising and was one of the early things causing excitement about second-class currents. This is what you would have predicted for the energy dependence if there were no second-class current. This would be just due to an effect called weak magnetism. And this is what was observed about twice what you expected. So this experiment published a result claiming that there seemed to be some evidence for a second-class current that was the order of the same size of weak magnetism. So, but after an early shakeout, no other experiment, and I believe there were 5 altogether, found any evidence for a second-class current greater than something like 20% of weak magnetism. And in principle, that neon-19 experiment should have been the very best that there is to investigate second-class currents. The caveat, however, is that it's sensitive to a measurement of the beta spectrum. And those of you who are sensitive to the history of nuclear physics know that depending on beta spectrum measurements can be a perilous endeavor. And at the moment, there's no explanation for this date, for their result. I spoke with Frank Calaprice and some 30, 40 years later, they still don't know what's happened. So this is an issue that I would say was not clarified. Now, Stuart spent some time at Princeton, then went on to Stanford, and we hired him back at Argonne in a time when you can see that HR did not play a big role in how one was able to communicate with the people you hired. And so merely asserting that, and writing down, he insisted that I write it down. Verbal was not good enough, that I would not screw him unnecessarily. And so it gives you some idea of what our relationship was like. He came. So the second clarification was there was a thing called a 17 kilovolt neutrino, and that went on for a period of several years, the order of 5, regarding evidence for a neutrino that had a mass of about 17 kilovolts and mixed in at a level of about 1% with the electron neutrino. And its presence was alleged to come from the spectrum of the following decays of tritium, sulfur, nickel, and carbon-14. Now, all the observations that required such a neutrino involved a measurement of the beta of the decay beta particle, measuring that in matter. Any of the magnetic measurements of the beta spectrum did not seem to show this effect, but nevertheless, the controversy persisted. So I'll show you what some of the evidence looked like. This is the decay of chlorine-35 in an apparatus. In this case, because this is, in a sense, a memorial session for Stuart, I'm going to focus on Stuart and not name any of the colleagues who might be guilty of having made some mistakes that allowed him to correct them. So this was a publication in Physics Letters of that decay. Here we have a sulfur-32 source, lots of appropriate collimators. It's detected in a silicon solid-state detector, and lots of, as I said, collimators to make sure nothing other than the beta particles from the source were deposited in the detector. And this is the result. So if you take the data and divide it by a fit, assuming that there is no mixing, that is, the sign of that mixing angle is set equal to 0, this is what the paper claimed, using the data here from I think it's 120 kilovolts and above. You fit the data in that region and try to fit it with 0 mixing, and of course you do very, very badly. You require a mixing angle the order of 1%. These are 2 runs basically of the same kind. Another approach is to make the same assumption and take the data out in this region to determine the beta shape. And sure enough, you see an additional contribution at the order, again, of 1%, and an energy that was 17 kilovolts below what you would have expected for a massless neutrino. The evidence for against this such a neutrino comes, and actually this involved a young man who was an undergraduate at the time, Jason Mortera, at the University of Chicago. You'll notice our chairman was involved also in this endeavor. And again, this is a measurement of the sulfur-35 decay in an apparatus that's really quite different. It involves actually measuring the electrons in a material detector, but in this case, the source is embedded in a magnetic field that's extremely strong. The field direction is along this direction, causing the electrons to spiral So you could focus, as it were, all the electrons into the detector without the use of any collimator, and the fact that the detector is placed out here meant that any electron that backscattered off the face of the detector due to the presence of this magnetic field would be forced back into the detector. This is the spectrum that was observed. Looks pretty clean. You need a fairly intense source, so there was some pileup at the end. This is the calibration from known conversion lines. And this is what they saw. So this is what would have been expected if the mixing was the order of 1% with a 17 kilovolt neutrino. Notice that the chi-squared for this many degrees of freedom is 2.8. When you assume that that mixing angle is 0, a much more satisfactory value of chi-square is obtained. Carbon-14 was introduced into this sample just to show the sensitivity that measurement was able to perform. This is the fit that they get, assuming that carbon-14 mixture is present, and they're certainly sensitive to that. And over here is a plot of the results of all the previous experiments claiming 17 kilovolt neutrinos versus the mass and the mixing angle, and these are the limits set up by the measurement that Stuart and colleagues at Argonne and Chicago pulled off. So there's a clarified issue. 17 kilovolt neutrino was gone. Now, the next thing that Stuart got involved in was looking at the issue of E plus E minus pairs from very heavy ion collisions. One achieved in the late 70s and early 80s the ability to accelerate very heavy ions to sufficient energies that you could really approach the Coulomb barrier. For example, the Coulomb barrier between thorium and uranium is the order of 800 MeV. So you needed fairly energetic ions to get these two nuclei close together. What one was looking for somehow was to pop positrons out of the vacuum, because transiently, as these two heavy ions came together, the central field they would generate was deep enough to have an electron jump in to the s orbit, and that came out of the Fermi sea, and that would then liberate a positron. Wasn't clear that such an effect was ever observed, but what was observed were basically pairs of E plus E minus that were in coincidence that seemed to come from some common particle that was moving roughly with the center of mass velocity of the heavy ion collision, and it was thought that it was possibly the decay of some unknown object that decayed into an E plus E minus pair. The kind of evidence that you had for such things is found in diagrams like this, in data like this. I think I'm running out of, well, maybe not so bad. Thank you. So this is the summed energy of the beta plus, or the energy, excuse me, of the beta plus, the energy of the electron, their summed energy, and the difference of their energies. So below are Monte Carlo calculations, one based on the fact that it would be due to a neutral particle, the other from internal pair creation. In internal pair creation, the effects of the correlation should be smeared because the nucleus can carry away both energy and momentum. So the key over here is the appearance of this peak at about 800 kilovolts in the kinetic energy of the summed positron and electron. If you look at their difference, you would expect it to center somewhere around 0, and indeed there seems to be evidence for a peak there, and the data looked a lot more like what one would believe, that it was the decay of a neutral particle rather than internal pair creation. Notice, however, that the statistics are really pretty poor in those measurements. So there was then a spectrometer called APEX. I'll just call it the argon. Is it argon? Proton, positron, electron experiment. Has a somewhat larger cast of characters. And the spectrometer that was used seems in some ways to use some of the ideas that Freedman had shown in his showing that the 17 kilovolt neutrino was not right. Again, the electrons and positrons came from out of the source, spiraled in a magnetic field in the direction in which they were to travel. They were then detected in a detector, a solid-state detector, and a sodium iodide array was able to tell which of the particles was a positron. With appreciably higher statistics. Can't seem to find, there we are. For different energies and particle types, the spectrum of the summed energies was taken, and lo and behold, there is a distribution with basically two different kinds of containment of conditions put on where the heavy ion collision was, at what angles they occurred at. And this was the peak that would be expected if the results from the GSI experiments that were finding such peaks were present. As soon as this work came out, there were two subsequent experiments at GSI showing an absence of peaks in their results also. So again, the E plus E minus dilemma was put to rest. On to a fourth clarification. So this one is really quite recent, and it involves oscillations seen in the probability of electron capture decay, in which the electron capture occurs in the decay of hydrogen-like praseodymium-140 and promethium-142. These things occur naturally and are relatively well understood. They decay by a combination of positron emission and electron capture in these two cases. The experiments were carried out again at the GSI. They were injected from I think it's samarium-152 is injected from the UNILAC, put into a synchrotron that boosts their energies to several hundred MeV per nucleon. They're then fragmented in a beryllium target, and a combination of energy loss, magnetic fields, selects out the particular mass and charge state of these ions, which are then put into an electron storage ring at GSI. And in the storage ring, one can sense the revolution time of actually single ions that have a charge greater than 30 with Schottky pickup probes. And this combination has been just absolutely remarkable in the number and accuracy of nuclear masses that they have ended up measuring. So basically pretty simple in the way that it works. The particles are brought in, cooled, takes something like about 10 seconds to cool, but after they cool, they are in this storage ring, and down here at the two ends, you can see particles, they're cooled to basically have the same velocity. So particles with greater mass undergo a longer flight path and hence arrive later at the Schottky pickup coil. So here's just an example of how beautiful this is. This is a metastable state of samarium relative to the ground state of samarium. That's 174 kilovolt separation, and this is their frequency as measured in that storage ring. Now, tracking the decay is a little harder matter. The ion charge remains the same in electron capture, but the mass has changed because you've gone to the ground state of a different nucleus. So this is an example with a single ion present in the storage ring. This is promethium. Boy, I can't see those numbers. Is that 140? Whatever it is, it decays and goes to a slightly different mass in this other final state. So this is a case that you have when you have two ions present in the ring, and one of them makes the transition, and the other either disappears via decay or some interaction in the ring. So they keep track of everything in that sense. And this is looking at the decay of promethium, and very differently from the straight exponential decay that one saw, there seemed to be some harmonic component present in it. When you analyze the data, I don't know how well you can read that, but this ends up with fitting the data with a amplitude, a frequency, and a phase. For the promethium, the amplitude is the order of 20%. The period omega turns out, or the angular frequency omega, it turns out to be correspond to a period of about 7 seconds, and the phase angle is set. The phase angle differs in the two cases, and you can imagine if something is going to undergo harmonic decay, you need to have a set phase angle. Where that knowledge would occur is really hard to say. So the period, as I said, is about 7 seconds. And if you want to account for that, you need an energy splitting the order of 10 to the minus 16 electron volts. You bet. Thank you, John. Really hard to come by. Now, the fact that there was a mixing the order of 20%, and one way you could get a number as small as 10 to the minus 16 is to basically take the splitting of the solar neutrino mass splitting between masses 1 and 2 and divide it by the mass of the decaying nucleus. So somehow claiming that in that decay these neutrinos and the nucleus to which it decays were entangled. Now, this number is about a factor of 3 away in terms of what you need in order to get the right energy splitting, but nevertheless, people were much attracted to that, and if this was a great way to measure neutrino mass differences in mixing, it sure was a heck of a lot easier than many of the experiments, the neutrino experiments that have been undertaking. And this reflects the ensuing controversy, the yeas and nays claiming it was possible for this entanglement to occur, and those who claim that it was absolutely impossible. So it's sort of equally split. If you look at if you sort of weighed things by reputation, you might say that the naysayers were heavier than the supporters. So in this case, out at Berkeley, they carried out an experiment creating the promethium-142 again in a heavy ion collision. In the Berkeley gaseous separator, it was put into a very thin foil, and the photons associated with their decay are measured. Here are the K alpha and beta lines that one sees. If you track then the electron capture events by the K alpha gamma rays, you get a decay curve which shows no evidence for oscillation. If you do a Fourier analysis, you can't find any period at about the right, what one wanted. The fluctuations are pretty amazing. So it's clear if you do a Fourier decomposition of a spectrum, you will get some pretty wild variations. However, the amplitude seems to be a total mismatch between what was observed at the GSI experiment. So in this case, the amplitude is the order of less than 1.5%, and if there's any period at all associated with it, it's at the order of 3 seconds. Now, I'm not entirely sure that this experiment disproves the GSI result, because when you have a full atom and capture that electron, that inrushing filling of that hole seems to me to involve times that would wash out any neutrino effects that are present. So if you just look at what Stuart's done, the areas in which he's worked and made really important contributions, all the way from astrophysics, experiments carried out at high energies, at SLAC, and the weak interaction in atomic physics. It's absolutely remarkable. I think this is a remark to me of his courage, as well as his smarts, that he was willing to tackle things that were often far afield from what he knew, but if he realized it was important, he was going to go about learning it. And so I would conclude by just saying, we could learn a great deal from Stuart. Following his example in terms of his integrity, breadth of knowledge, and interest makes him a model for all of us. Thank you. Oh yes, but that wasn't resolving an issue. I didn't think. No. And besides, that territory was going to be covered far more ably by the next speaker.